So think about this, right? If it's concave up, what can you say about the derivative? Study the derivative function on a concave up function. What does it look like? Think about little tangent lines as you trace along the graph, right? Think about little tangent lines as you trace along the graph. What are you looking at there? I usually try to draw them in with just like little line segments, right? I got like a little tangent line, a little tangent line, a little tangent line, and of course they extend, but little tangent line. And well, it's negative. It's negative. This one's 0. This one's positive. This one's positive. So what's happening? The derivative is increasing as we go through a bowl shape, which is why that theorem is true. All right? And if you look at a concave down one, what's the opposite story, right? So you've got positive slope, you got 0 at the top, you got negative slope, see, the derivative is positive to 0 to negative. The derivative is decreasing for this, right? We should do some graphing of the function, the derivative, and the second derivative all in one picture. I haven't done that for you guys yet. I should do that sometime soon, yeah? Okay, so let's go back to our example 5.1.20. Where is it concave up? Where is it concave down? Something else I should tell you. The point on a function which changes from concave up, where there's a change in concavity, this is called a point of inflection. So like this point right here in my example, this is a inflection point. So this example back over here, I'm going to, I guess I can work in here. What's f prime prime of x? It is 2x plus 1. Second derivative is just 2x plus 1. So 2x plus 1 equals to 0 when? Minus a half, right? So if I make a sign chart for the second derivative, there's just one critical number to worry about on there. I shouldn't say critical number. I use the word critical number for the first derivative only, all right? Places where the second derivative 0 is not a critical number, I would call it a possible point of inflection, all right? But anyway, minus a half. And you think about this, so if I plug in 0, I get 1, right? Wait a minute. If I plug in 0, I get 1, so it makes positive over here, right? Concave up, it's negative over here. So this function is concave up on minus infinity, good grief, minus 1/2 to infinity. It's concave down on minus infinity to minus a half. And at x equals to minus 1/2, we have a point of inflection. So if you're careful, you can use this to vastly improve the quality of your graph. See, because my picture over here, and I almost had it right. Maybe I had it right, I don't know. This isn't quite to scale, right? But at minus 1/2, right, minus 1/2 right there, I should have the graph going from being like upside down bowl shaped, right, to concave up, right side up. So I'd make it a little bit more like that. So it's a real subtle change to my graph in this case, you know, because I was kind of close to it already. But including points of inflection on a graph, including where it changes from upside down bowl shaped to right side up bowl shaped, that does improve the fidelity of your graph, if you will. Any questions? Let's look at an example. Here, this is good. We haven't done one that's this ugly. It's probably be good for us to do this. Before I do the ugly one, I'll do an easy one though. If we had f of x equal to x cubed, then f prime of x is 3x squared, and f prime prime of x is 3x. So this is kind of a nice example in the sense that we have the same 0 is the critical number for the derivative, right? But it's also the possible point of inflection for f prime prime. So when you plug in points to 0 here, it's always positive. So this is case 3 of the first derivative test. It's neither a max nor a min, right? On the other hand, here we go negative, positive, right? And so this is the cubic, It's concave down, hits 0, and becomes concave up. All right. One more easy example. F of x equals to x to the 4th. So f prime of x equal to, I want x squared. I'm sorry, x to the 4th is too much. F prime of x is 2x. F prime prime of x is 2. So there's just 0 for f prime of x, right? And it changes from negative to positive. And how about the f prime prime of x? There's no place at 0, right? It's just always 2, right? And so we already know the graph, right? It's what? X squared. So f of 0 is what? It's a local, indeed a global, minimum. By the way, this gives you an example of what's called the second derivative test. The second derivative test it says that if f prime of c equals to 0, right, then if f prime prime of c is less than 0, then max. If, on the other hand, f prime prime of c is greater than 0, then min. I'm being a little bit glib in my speaking here, yeah? And if f prime prime of c equals to 0, I know nothing. So no comment. So notice that like f prime prime of 0 here equals to 0 in this previous example. So like the second derivative test does not apply in this example at the critical number because f prime prime is 0. It says the case that the second derivative test says nothing. The second derivative test says it's positive. If the second derivative is positive, it's a minimum. If the second derivative is negative, it's a maximum. See, this says second derivative positive, too, and it's a minimum, right? So the first derivative test, on the other hand, is not silent ever. It tells you max, min, or neither. All right. So second derivative test is useful, but it is somewhat limited in its application. But it is straightforward and geometrically obvious once you understand. I mean, what does it mean? F prime prime negative, that means it's concave down close to the critical point. So it's like this. So yeah, it's a max, right? F prime prime positive means it's like a bowl shaped up, right? So it's definitely going to be a min. It makes total sense why the signs are flipped. But it is always a temptation of students to assume that f prime prime less than 0 means min. That's just not true. Okay. All right. Oh, now I don't have time for my interesting example. So sad. Let's see here. Well, I think I took you guys 2 minutes over the other day, so let's end 2 minutes early today. How's that sound? Thanks, guys.